Hello, my name is Jay Lim, and I'm a PhD student at Rutgers University with my advisor Santosh Nagarakate. Today, I would like to show you an exciting method for generating approximations of elementary functions for 32-bit representations. All endeavors in science, from structural engineering to high-performance computing, machine learning, and scientific simulations, use math libraries to approximate elementary functions like natural log of x and sine of x. Unfortunately, mainstream math libraries do not produce correct results, which can lead to catastrophic consequences. So the goal of our work is to generate approximations of elementary functions for 32-bit representations that produce correctly rounded results for all inputs. In the context of the RLibN project, our prior work, we have been making a case for approximating the correctly rounded results rather than trying to approximate the real value of the elementary functions. And if you do that, you can use linear programming to generate polynomial approximations. To make this applicable for 32-bit representations, we make three contributions. First, instead of trying to generate a single polynomial for all inputs, we generate a piecewise polynomial. Second, we use a program synthesis-inspired technique to generate polynomial approximations using a handful of inputs. Third, we propose methodologies that support various range reductions. The resulting math library not only produces the correctly rounded results for all inputs, but is faster than mainstream math libraries that have been optimized for decades. So let me first start off by describing what correctly rounded result is. Consider this real number line here. 32-bit float can only represent finitely many values. So if you can't exactly represent a value like natural log of x1 in this blue value, then you have to round it to a 32-bit float value, which in our case is the green v1. So v1 is the correctly rounded result of natural log of x1. An approximation function that produces the correctly rounded results for all inputs is called the correctly rounded approximation function. And a math library where all approximation function is a correctly rounded approximation function is called the correctly rounded math library. Now, to describe how mainstream math libraries approximate elementary functions, consider the function sine pi of x on the left side. Sine pi of x is equivalent to sine of pi times x. Similar to the sine function, sine pi of x is also a periodic function, but with a period of size 2. And it has all the trigonometric identities that sine function has. In high level, the most common method for approximating elementary functions is with polynomials, something like this. All mainstream math libraries use the minimax approximations to generate polynomials that approximates the real value of the elementary functions. The state-of-the-art minimax method is the Remez algorithm and its variants. The polynomial is then evaluated in a higher precision representation compared to the target 32-bit representation, like the double representation, to produce more accurate results. However, polynomial alone is not sufficient to generate accurate results for all inputs. If you look at this graph, our polynomial approximates sine pi of x accurately for inputs between 0 to 0.5, but as the input gets larger, the error increases significantly. So math libraries typically use range reductions to transform any arbitrary input into a reduced input in a small domain. Let me show you a simple example of range reduction for sine pi of x. Sine pi of x is a periodic function where each period is exactly the same. And inside of each period, there are 4 quadrants that are exact mirror image of each other. So we can use these trigonometric identities to transform any input to a reduced input between 0 and 0.5. Consider an example with inputs 1.6. Using trigonometric identities, sine pi of 1.6 can be computed with minus sine pi of 0.4. So we can first take the input 1.6 and reduce it to the reduced input 0.4. And then we can use polynomial to approximate sine pi of 0.4. The result of the polynomial approximates the reduced input instead of the real input. So we compensate the output of the polynomial using the output compensation function to get the final result. This range reduction reduces the entire input domain into a smaller domain between 0 and 0.5. So we can use a polynomial that approximates sine pi of x accurately between 0 and 0.5 to approximate sine pi accurately for the entire input domain. Although mathematically, in the real number settings, it makes sense to approximate the real value of the elementary functions, in the context of finite precision representations, this creates several challenges. Let's go back to our real number line. Sine pi of x1 is relatively close to the midpoint between v1 and v2, or two adjacent 32-bit float value. Since v1 is a correctly rounded result, the approximation function should produce a value within this gray area so that the result rounds to the correctly rounded result, v1. But because minimax approximation approximates the real value of the elementary function, in reality there's only this much room for error. So mainstream math libraries have to use very accurate polynomial approximations and have to make sure that numerical error that occurs from evaluating the polynomial and the range reduction is extremely small, or otherwise it'll produce the wrong results. So instead of trying to approximate the real value of f of x, our prior work, the RLibM project, has been making a case for approximating the correctly rounded results of the elementary functions. The key insight is that there's a range of value in the vicinity of v1 where if the approximation function produces any value within this interval, the result will round to the correctly rounded result. We call this interval the rounding interval. So RLibM has been generating polynomials by first computing the correctly rounded result for each input, and for each other result, the rounding interval for them. The graph on the right side shows a rounding interval for each of the inputs with the gray boxes. Now our polynomial should produce a value in the rounding interval when it is used with the range reduction. So we infer the values that our polynomial should produce based on the rounding interval that we computed and the range reduction, and restrict this interval to account for the numerical errors that occurs when we evaluate the range reduction. We call this interval the reduced interval. The reduced interval defines constraints on the values that our polynomial should produce. So we frame the problem of generating a polynomial as a linear programming problem and use a linear program solver to generate a polynomial approximation. But now our question is, how do you make this work for 32-bit representations? In 32 bits, there are 4 billion inputs. The most complex and advanced range reduction may reduce the number of inputs to millions of reduced inputs, but LP solvers cannot feasibly handle millions of constraints. Additionally, 32-bit representations have higher precision, which requires a higher degree polynomial to approximate accurately, leading to slower performance. To address these challenges, we make 3 contributions. First, we propose a methodology for computing the reduced intervals for complex range reductions that use multiple approximation functions. Second, we want our polynomials to be fast. One way to generate polynomials that is efficient to evaluate is to generate a piecewise polynomial where each polynomial has lower degree, rather than trying to generate a single high-degree polynomial for the entire input domain. Third, we use a counterexample-guided polynomial generation technique inspired from program synthesis. Now let me go through each of these 3 techniques and briefly explain them with an example of generating an approximation function of sine pi of x for 32-bit float from inputs between 0 to 0.5, where we evaluate the approximation function with the higher precision double representation. First, because 32-bit representations have 4 billion inputs with wide dynamic range, we want to use complex range reductions to significantly reduce the input domain. But these range reductions may use multiple approximation functions, which makes computing the reduced intervals difficult. For example, consider the sine pi of x functions for inputs between 0 to 0.5 on the right side. The first thing that we can do is to filter out some special case inputs. There are inputs near 0 where computing pi times x produces the correctly rounded result. Once you eliminate these special cases, we're left with 190 million inputs ranging from roughly 10 to the power of minus 7 to 0.5. To reduce the input domain even further, we can use this trigonometric identity. We can split the input x into a plus b, where a is a continuous variable ranging from 0 to 1 over 512, and b is a discrete variable where the values are a multiple of 1 over 512. Since there are exactly 257 values for the discrete variable b, we can create a lookup table for cosine pi of b and sine pi of b. Then sine pi of x can be computed with a times sine pi of a plus b times cosine pi of a. Thus, to approximate sine pi of x, we first reduce our input x into the reduced input a, and approximate sine pi of a and cosine pi of a with polynomial approximation. Because our polynomial produces approximations for the reduced input a, we compensate the output with the formula a times sine pi of a plus b times cosine pi of a to produce an approximation of sine pi of x for the original input x. This formula is called the output compensation function. So our range reduction significantly reduces the input domain to 0 to 1 over 512, but our output compensation function requires us to approximate both sine pi of a and cosine pi of a. To make sure that the result of our output compensation function produces a value within the rounding interval, we have to identify the reduced intervals for both sine pi of a and cosine pi of a, where these reduced intervals are dependent on each other. So we propose a methodology for identifying reduced intervals by initially setting the interval with a singleton of the real value of sine pi of a and cosine pi of a, and gradually lowering the lower bound of both intervals at the same time while making sure that the lower bounds will produce the correctly rounded result when it is used with output compensation function. Similarly, for the upper bound, we gradually increase the upper bound of both reduced intervals at the same time while making sure that the upper bound will produce the correctly rounded result when it is used with the output compensation function. If the output compensation function is a monotonically increasing function, like in our example, our methodology guarantees that any value in the reduced interval will produce the correctly rounded result if it is used with the output compensation function. Once the reduced intervals for sine pi and cosine pi is computed for all inputs, then we need to generate a polynomial approximation for sine pi of a and cosine pi of a. Let me continue with focusing on generating an approximation function for sine pi of a, where the reduced intervals are shown on the right side. There are still roughly 100 million reduced inputs in our reduced input domain. So instead of trying to generate a single polynomial for the entire 100 billion reduced inputs, our second technique generates a piecewise polynomial by splitting the reduced input domain into multiple subdomains and generating a polynomial for each subdomain. With piecewise polynomials, each polynomial will have lower degree, thus increasing the performance during evaluation. To efficiently identify which polynomial to use for each input, we split the input domain based on the bit string of the reduced input in the double representation, which is the representation we use to evaluate the approximation function. All of our reduced inputs have the same bits in the first 6 bits in the bit string. So we group all the inputs that have the same bits in the 7th and 8th bits into the same subdomain. This allows us to identify which subdomain to use for each input by just using a single AND operation and a shift operation, allowing us to efficiently retrieve the polynomial that belongs to the subdomain number 2. Finally, even the splitted subdomain may contain millions of reduced inputs, and LP solver cannot feasibly handle millions of constraints. So we propose counterexample guided polynomial generation technique inspired from program synthesis. First, we choose a sample of constraints and use just these constraints to generate a polynomial that satisfies all the constraints in the sample. Next, we check whether the candidate polynomial satisfies all the constraints in the subdomain. And if it does not, we identify those constraints and add them to our sample. Then we repeat the process of generating candidate polynomials with the new sample until the polynomial satisfies all the constraints in the subdomain. For more information in our technique, please refer to our paper. Using these techniques, we created R1132, a correctly rounded math library for 32-bit float and 32-bit posit representations. Currently, R1132 has 10 elementary functions for 32-bit float and 8 functions for 32-bit posit. We're working on other functions as well. We used an MPFR math library with at least 200 precision bits to compute the correctly rounded results. All of our experiments were performed on a machine with 2.1 GHz Intel CPU running Ubuntu 18.04. In our experiments, we were interested in 2 questions. Does R1132 produce correctly rounded results for all inputs? And how fast is R1132? To measure the performance, we compared RLibM32 against Intel and glibc's float and double math library, as well as crlibm. Both glibc and Intel math libraries are widely used, and crlibm is a correctly rounded math library for the double representation. To use double math library for our 32-bit representations, we first converted 32-bit input into a double input, used the double math library, and converted the result back to the 32-bit representations. In this presentation, we show you the results of our experiments for 32-bit float functions. To see the full evaluation results, please refer to our paper. Our experiment shows that all of our 32-bit float functions in RLibM32 produces the correctly rounded results for all inputs. In contrast, both float and double math libraries in glibc, Intel, and crlibm do not produce correctly rounded results for all inputs. In some extreme cases, mainstream math libraries for float produce wrong results for millions of inputs. Our experimental evaluation also shows that RLibM32 is fast. For each elementary function, this graph shows a speedup of RLibm's float math library functions against glibc's math library. Speedup over 1x indicates that RLibm32 functions are faster. On average, RLibm32 has 1.1x speedup over glibc's float math library and 1.2x speedup over glibc's double math library. Compared to Intel math library, RLibm32 float functions have an average of 1.5x speedup over Intel's float math library and 1.6x speedup over Intel's double math library. In our experiments, we found out that Intel math library is more accurate than glibc math library, so RLibm32 has higher speedup over Intel math library. Finally, RLibm32 has 2x speedup over crlibm functions on average. Since crlibm is a correctly rounded math library for the double precision, RLibm32 has the most speedup over crlibm. Overall, our experiment shows that RLibm32 is faster than mainstream math libraries and produces correctly rounded results for all inputs. On the other hand, mainstream math libraries do not produce correctly rounded float results for all inputs. In conclusion, we make a case for approximating the correctly rounded result rather than approximating the real value of the elementary function, and use LP formulation to generate polynomial approximations. To make LP formulation feasible for 32-bit representations, we propose 3 new techniques. First, instead of trying to generate a single polynomial, we generate a piecewise polynomial. Second, we use a counterexample-guided polynomial generation technique inspired from program synthesis. And we propose a methodology that supports various complex range reductions. The resulting math library not only produces correctly rounded results for all inputs, but is faster than mainstream math libraries that have been optimized for decades. Our long-term goal is to make correctly rounded math library mandatory rather than a recommendation by the standards. Thank you very much. RLibm32 is open source, and we are continuously making more elementary functions and improving them, so please give them a try.